All right, ready for more work? Here we go. Problem number 10. For each of the following polynomials, list all the possible rational zeros. And then we're going to find all the zeros, and then we're going to write it as a product of linear factors. Okay, here we go. So we know we have 3 zeros, right? Because this is degree 3. This is all multiplied out. Unfortunately, it is not factored for us, which means we have to do all the steps for finding the zeros. There's no greatest common factor. There's no cute tricks for handling this, so I'm going to just jump right in and list all possible rational zeros. All right, so to do that, I often call it P over Q. It really doesn't matter what you call it. The top is all the factors of the constant, which is 36. There's a lot of numbers that divide into 36. 1, 2, 3, 4, 5 doesn't, 6 does, 7 doesn't, 8 doesn't, 9 does, 10, 11, 12 does, and then, even 18 and 36. Can't forget the one at the end. Over plus or minus 1, which comes from the leading coefficient. So your list, when I do the list for all possible rational zeros, because we're dividing by 1, it really is just the numerator. There we go. So that answers question A. All right. B, find the zeros. Y'all, that's where all the work comes in. Right. So what you need to do is you do your synthetic division table. I really don't have enough space right here to do it, but I'm going to start it anyway and just hope that I find a zero before doing too much work. You write your list of coefficients. 1 represents x to the third. Negative 7 represents x squared. There is no x, so I need to put 0 to represent the x, and then 36 for the constant. Y'all, I'm just going to start with number 1 on this list and just see if I can find a 0. So I'm going to talk you through all of it. The 1 comes straight down. 1 times 1 is 1, plus negative 7 is negative 6. 1 times negative 6 is negative 6, plus 0 is negative 6. 1 times negative 6 is negative 6, plus 36 is not 0, so 1's off the list. I'm going to check negative 1. 1 comes down. Negative 1 times 1 is negative 1, plus negative 7 is negative 8. Negative 1 times negative 8 is 8, plus 8 is 8. My brain's working faster than my mouth. Negative 1 times 8 is negative 8, plus 36 is 28. You know what? Also not a 0. So I told you I made my synthetic division table too close to the end. So I'm going to start a new table. 1, negative 7, 0, 36. Next number I'm going to check is 2. 1 comes straight down. 2 times 1 is 2, plus negative 7 is negative 5. 2 times negative 5 is negative 10, plus 0 is negative 10. 2 times negative 10 is negative 20, plus 36 is 16. Basically, that's not a 0. I'm going to check negative 2. 1 comes down. Negative 2 times 1 is negative 2, plus negative 7 is negative 9. Negative 2 times negative 9 is 18. Hey, this is looking good. Is 18 plus 0 is 18, and negative 2 times 18, woohoo, is negative 36 plus 36 is 0. Now y'all know why I put yay at the end of these when I find zeros. Negative 2 is a 0. Okay? Now that's good news. Always, always, don't keep doing with this division table and start checking all these numbers, because that does not get you what you need. You need to stop and rewrite your problem. So P of X is partially factored now. Why? Because negative 2 is a 0, which means x plus 2 is a factor, times your quotient right here. Remember, constant remainder, constant x squared. So this is going to be x squared minus 9x plus 18. Does that factor? Are there numbers that multiply to be 18 and add to be negative 9? There are, and I'm going to continue in orange just so you can follow. So I'm coming bottom right of the screen. P of x equals x plus 2 times, multiplies to be 18, adds to be negative 9 is x minus 3 times x minus 6, right? Hey, that's already, that's the answer to C. This is what we call a product of linear factors, because they're linear because they're all x to the first power, and they're factors because they all multiply together to give you the original polynomial. The zeros, on the other hand, we've already found one of them, -2, and it comes from that factor right there. So x equals -2, x is equal to 3 from here, and x is equal to 6 from the third factor. And there's all 3 of your zeros. How'd I know I only have 3? Because this is a degree 3, right? Okay, let's try another one. Now let's try this again. This one might be a lot more rough. Look, it's a degree 5. So I'm looking for 5 zeros, which means we might do a whole lot of synthetic division before we finish this problem. But that's okay, we got this. So if we want to make our list, y'all, I'm going to make it at the top of the screen up here. So P over Q, remember, is all the factors of the constant, which is 10. Anything that goes evenly into 10, 1, 2, 5, and don't forget the number itself, 10. And the denominator is the leading coefficient. Anything that goes evenly into 1, so that's 1 and 2. Now when you make your list, you have to combine these every way possible. So I have to put 1 over 1, which is plus or minus 1. I also have to put 1 over 2, which is plus or minus 1/2. So I'm finished with the 1 over. Now let's do 2 over. 2 over 1 is plus or minus 2. 2 over 2, y'all, is plus or minus 1. I already got that on the list, so I'm not going to write it again. Then I move over to 5. 5 over 1 is plus or minus 5. 5 over 2 is plus or minus 5/2. Move over to the 10. 10 over 1 is plus or minus 10. 10 over 2 is plus or minus 5. We've already got that on the list. So there is your list of possible rational zeros. Now, all 5 of these zeros may be on the list. Some of them might be irrational numbers, like 1 plus the square root of 2. Or some of them might even be imaginary numbers like 3i. Okay? So don't think that all 5 numbers are going to be on the list. They might, but we don't know that. Now I'm going to come down here and start checking the list, right? So my coefficients go across the top. Okay, make sure everybody's represented. There's a 5, a 4, a 3, a 2, a 1, constant. Everybody's there. So I'm going to list the coefficients. 2, -3, -6, 23, -26, and 10. Okay? What out front? Just start with your list. I'm going to check 1. I always check positive 1 first. So 2 comes down directly. 1 times 2 is 2, plus -3 is -1. 1 times -1 is -1, plus -6 is -7. 1 times -7 is -7, plus 23. Gotta think about that for a minute. 16. 1 times 16 is 16, plus -26 is -10. 1 times -10 is -10, plus 10 is 0. Y'all, that's awesome. We already have a 0. X equals 1. Do you want to continue this table checking numbers? No, you do not. Don't keep going because you're not going to get your problem factored like you need. You have to stop and rewrite. So right now we're P of X equals, look, my first factor, my first 0 is a 1. So my first factor, I'm just going to put X minus 1. Times, remember, this is a coefficient. These represent coefficients. There's remainder, constant, X. X squared, X to the third, X to the fourth. And that's what we've got to write. So I now have 2X to the fourth minus 1X to the third minus 7X squared plus 16X minus 10. Y'all, if I knew how to factor that, I'd sure do it, but it's an X to the fourth. Which means we need to start synthetic division again. So I'm going to start another table. I probably don't have enough room at the bottom of the page, but whatever. That's all I got. So I'm not going to use my original coefficients. Now I'm working on this right here. Okay? That's going to go across the top. It also matches the numbers I had on my last line. So 2, -1, -7, 16, -10. Where I'm going to start here, -1, you say, no, start where you left off. Because 1 might very well be a 0 again. Remember multiplicity? When some numbers show up as zeros more than one time. So check where you left off. 2 comes down. 1 times 2 is 2, plus -1 is 1. 1 times 1 is 1, plus -7 is -6. 1 times -6 is -6, plus 16 is 10. 1 times 10 is 10 plus negative 10 is 0. Whoo-hoo, look, we've got another 0, okay, right there. So 1's a 0 again. So I stop and I rewrite. Now I'm going to switch colors on you so you can follow what I'm doing on this tiny little page. I'm rewriting up here. This is P of X equals. I've already had an X minus 1. I'm recopying that one. The pen's got a delay. I have an X minus 1 here, so that's my new one. Times my coefficients. So remember, this is remainder. This is X squared, X to the third, and X. Ooh, no. I skipped. Constant. X squared, X to the third. There we go. So that's 2X to the third minus plus X squared minus 6X plus 10. Now, that's got 4 terms. If factor by grouping would work there, I would do it, but it doesn't. So you know what I got to do? I got to start a new synthetic division table. Is that all right? Nah, yeah. I'm tired, right? But that's what we got to do. So this is 2, 1, negative 6, 10. Where do I want to start? Hey, you know what? 1 might be a 0 even a third time. We got to try it. So 2 comes straight down. 1 times 2 is 2 plus 1 is 3. 1 times 3 is 3 plus negative 6 is negative 3. 1 times negative 3 is negative 3 plus 10 is 7. So 1 is not a 0 a third time. Is that okay? Sure is. Now I'm going to check negative 1. So 2 comes down. Negative 1 times 2 is negative 2 plus 1 is negative 1. Negative 1 times negative 1 is 1 plus negative 6 is negative 5. Negative 1 times negative 5 is 5 plus 10 is 15. So negative 1 is not a 0. Now, if you want to check 1/2 next, you can, or you can start with the whole numbers. I'm just going to go ahead and check 1/2. Okay, but a lot of times I skip it and move on to 2 and negative 2, but I'm just going to go ahead and check 1/2. 2 comes down. 1/2 times 2 is 1 plus 1 is 2. 1/2 times 2 is 1 plus negative 6 is negative 5. 1/2 times negative 5 is negative 5/2 plus 10 is not 0. You know what? I don't even care what it is. I know it's not 0. So I'm going to check negative 1/2. Okay, 2 comes down. Negative 1/2 times 2 is negative 1 plus 1 is 0. Negative 1/2 times 0 is 0 plus negative 6 is negative 6. Negative 1/2 times negative 6 is 3 plus 10 is 13. Okay, so 1/2 is not a 0. Negative 1/2 is not a 0. I'm going to move on to 2. Now, I'm running out of page, so I've got this page. Got another page for this. So keep in mind, we've got the 1 zeros, and I'm going to recopy 2, 1, negative 6, 10. So next, I'm going to check my next number on the list, which was 2. So 2 comes straight down. 2 times 2 is 4 plus 1 is 5. 2 times 5 is 10 plus negative 6 is 4. 2 times 4 is 8 plus 10 is 18. So not 0, 2's out. Let's check negative 2. 2 comes down. Negative 2 times 2 is negative 4 plus 1 is negative 3. Negative 2 times negative 3 is 6 plus 6 is 0. Negative 2 times 0, 0 plus 10 is 10. So negative 2 is out. Okay. Now I'm going to tell you this problem is evil. I had to stop the video to find out what it was. And listen, you can check 2, negative 2. You can check 5 and negative 5. You can check 10, negative 10, and we'd already checked 1/2. You know what it is? Finally, negative 5/2. It's just evil. Don't worry, I would not do this to you on a test. Look, let's do it. 2 comes down, okay? Negative 5/2 times 2 is negative 5, plus 1 is negative 4. Can't write. Negative 5/2 times negative 4. What happens is the 2 and the 4 cancel to give you a negative 2 times negative 5 is 10, plus a negative 6 up there is 4. And then 2 goes into 4. 2 times negative 5 is negative 10, plus 10 is 0. I say finally, I cheated, because I just couldn't stand it. It's negative 5/2. Again, I won't make it so bad on the test, but it is worth doing this problem just for the frustration. Now you got to stop and rewrite. Remember what we have is p of x. We'd already found two zeros, and we wrote x minus 1 times x minus 1. Now we found another one, x minus 5 halves, times, here's our quotient right here, which is 2x squared minus 4x plus 4. Now there's a greatest common factor there of 2. That needs to come out. It's going to leave me with x squared minus 2x plus 2. And if it would factor, I would do it, but it won't. I have to use the quadratic formula. Of all things, now I have to use the quadratic formula. So I have x is equal to negative b, which is negative 2, plus or minus the square root of negative 2 squared, minus 4 times a is 1, c is 2. And that's all over 2 times a is 1. Notice this 2 right here, it's not going to matter as far as your zeros go. I'm not using that for anything. I'm using 1 for a, negative 2 for b, and 2 for c. Okay, let's simplify this thing. So that gives me 2 plus or minus the square root of 4. Minus 4 times 2 is 8 over 2. I keep scooting to the right. 2 plus or minus the square root of negative 4 over 2. Underneath, that's 2 plus or minus 2i over 2. And then where we talked about simplifying, if there's a number that would divide into all three of those, which is 2, I do that. So this is 1 plus or minus I over 1, or 1 plus or minus I. Oh my goodness. So if we list the zeros, remember we got x is equal to 1 and 1 twice. We got x is equal to negative 5 halves, and we got x is equal to 1 minus I and 1 plus I. Notice that is all 1, 2, 3, 4, 5 of our zeros. If you write that as a product of linear factors, you really can't, because it has this quadratic factor right here that won't break down. So that's as good as you can get by writing it as a product of factors. Okay? Oh my goodness, that was a big old problem. Okay, let's keep moving along. Maybe this problem, it won't be so difficult to find all of our zeros. But remember, it's not a hard process. It's just a long process sometimes. So notice we have a polynomial that's a degree 4. The highest exponent is 4. Look, this is all multiplied out. It's not in factored form, so there is no reason to add 4 plus 3 plus 2. You don't do that. The degree is 4. Okay, what does that mean? It means we're going to have 4 zeros. We can expect to have 4 zeros. Okay, now, if this was factorable just as it is, we would go ahead and factor it and move on. But we don't know how to easily factor degree 3 and higher polynomials. Sometimes when there's only 4 terms, you could do factor by grouping, but not the case here. So what do? Well, we list all the possible rational zeros. Remember, I write that as P over Q. You don't have to write that, but what you do need to do is put all the factors of the constant. What's the constant? 2. All the factors of 2 go in the numerator. So plus or minus 1, plus or minus 2. Again, if I highlight that, that comes from the green 2 down here. Now, what goes in the denominator is all the factors of the leading coefficient. What's the leading coefficient? Well, it just happens to be 2 in this case also. So that's plus or minus 1 and plus or minus 2. Again, where did that come from? Comes from the leading coefficient. So the constant goes on top, anything that divides evenly into 2. The leading coefficient goes on the bottom, anything that happens to divide into 2 again. Now you combine these every way possible. So y'all, when you make your list is not this fraction that I have written here, because that's not truly a fraction. That's a bunch of numbers over a line and then a bunch of numbers. You see what I mean? So to get your true list, what you're trying to do is write the number in the numerator over the number in the denominator every way possible. So I'm going to do 1 over 1 to start with. The plus or minus you don't have to separate, not for me. And then I do 1 over 2. So that's plus or minus 1/2. Then I do 2 over 1. So that's plus or minus 2. And then I do 2 over 2. But you know what? 2 over 2 reduces to 1, and I've already got 1 on the list, so no need to relist. Now, if you were typing this in the homework, I bet they don't want the plus or minus together. So if I list that, that would be 1 and negative 1, 1/2 and negative 1/2, and 2 and negative 2. And notice that's not in any particular order. I just wrote the positive number first and the negative number second, but they're not from smallest to largest. I don't think that's required. Now, what do you do with that list? By the way, that answers question 1. Now, what do you do with that list? Well, you draw yourself a synthetic division table. Now, what goes in the top is what you're trying to factor right here, which are the coefficients of this polynomial. So just to be very, very clear, what are coefficients? Those are those numbers in front. So 2, I want green. Okay, so 2 for the x to the 4th, 3 for the x to the 3rd, negative 4 for the x squared, negative 3 for the x, and then finally 2 for the constant. Please notice that I'm not missing any exponent. I've got my 4th, my 3rd, my squared, my first, and my constant represented. So I don't need any dummy variables or zeros listed down here. So I'm going to write the 2, the 3, the negative 4, the negative 3, and the positive 2 in order. Now what goes out front are the numbers that I'm trying to see if they're actually zeros. So I'm going to start with positive 1, but you could start with any number on that list that you would like. I always start with positive 1. So the 2 comes directly down, and you're doing synthetic division. 1 times 2 is 2 plus 3 is 5. 1 times 5 is 5 plus negative 4 is 1. 1 times 1 is 1 plus negative 3 is negative 2. And 1 times negative 2 is negative 2 plus 2 is 0. This is not like the last problem, right? Well, actually, the last problem we found zeros quickly, but then the remaining zeros were hard to find. So that may be the case in this again, too. You might want to circle that that's a 0, okay? I wouldn't bother to circle it if I didn't get a 0 remainder. But when you get a 0 remainder, then it's great. You stop. Don't pick another number on this list and start testing again, because you may not be able to get it completely factored that way. You want to stop and rewrite. So our original polynomial, I'm just going to call it p of x, because that's what they call it, equals. Now, this is going to be your divisor right here. Now, 1 is not your divisor. 1 is your 0. The divisor is going to be x minus 1. And that's one of your factors because the remainder is 0. So this is always a divisor. X minus whatever that is a divisor. But we know it's a factor when we get a 0 remainder. Now I'm going to multiply that times your quotient. What's the quotient? These values here, but that's not in quotient form, right? This is remainder, constant. There's my x squared, and my x to the 3rd term. So I'm going to write that down. That's 2x to the 3rd plus 5x squared, because the 5 is positive, plus 1x, because the 1 is positive, minus 2. Now, if this would work with factor by grouping, in other words, group these two together and pull out an x squared, that would leave 2x plus 5. Put these two together and pull out a 1, but the problem is it doesn't leave 2x plus 5. So there is no factor by grouping that'll work here. What does that mean I have to do? That means I have to do another synthetic division table. Okay? What goes at the top? Not your original polynomial, y'all. It's where you left off. So 2, 5, 1, negative 2. Notice that matches what this row is right here. 2, 5, 1, negative 2, which represents this polynomial. Now, what do I start testing down the side? Start where you left off. Don't check negative 1 now. Check 1 again. Maybe it's a 0 again. Okay? So the 2 comes down. Then I have 1 times 2 is 2 plus 5 is 7. 1 times 7 is 7 plus 1 is 8. And 1 times 8 is 8 plus negative 2 is 6. Now, what do I know? That 1 is not a 0 a second time. Okay? So I keep going. Now, what I really do is I'd keep going down if I had more room, but I don't. So I'm going to come over here and just rewrite 2, 5, 1, negative 2, and start with the next number on my list, which is negative 1. 2 comes directly down. Negative 1 times 2 is negative 2 plus 5 is 3. Negative 1 times 3 is negative 3. Plus 1 is negative 2. And negative 1 times negative 2 is 2 plus 2. Negative 2 is 0. Yay! I got another 0. Okay, so that means I need to stop and rewrite. It also means I drew my line too long, so I'm going to erase a little bit of that line because it's just in my way. There we go. All right, now, what did we just find out? Okay, there's my quotient right there, and there's my 0. So this is my remainder constant x squared. You're just building your way up. Or you know that you took an x to the third and you divided it by an x to the first, and that knocks that down 1 degree. So now I stop and rewrite my polynomial again. So here I go, p of x is now equal to the x minus 1 that we had to start with. How about that new factor? That's the 0. The new factor is x plus 1 times 2x squared plus 3x minus 2. Okay, now it is 2x squared plus 3x minus 2 factor. Maybe, okay, you could try the AC method, multiplying 2 times negative 2 and other numbers that multiply to be negative 4 and add to be 3, and there are, or you could use the quadratic formula. So if you're a good factorer, you will notice that, I'm just rewriting right now, but I'm going to factor that last polynomial, okay? Now I'm going to do the guess and check method. The only way to multiply to be 2x squared is with a 2x and a 1x. Okay? The only way to multiply to be negative 2 is with a 2 and a 1. But I've got to figure out where to put them. Okay? So if I put a 2 here and a 1 here, will that work? Because I have to multiply 2x times x is 2x squared, 2x times 2 is 4x. But I have to subtract the 1x to get that, and then that must be a plus 2 there. Try it. 2x times x is 2x squared, 2x times 2 is 4x, negative 1 times x is negative 1x, added to that 4x is 3x, and negative 1 times 2 is yes. Okay, now I need to move this information to the next page so we can finish this problem. Now, just so you know, that answers the third question. And sometimes you get the third answer before you get the second answer, because this is a product of linear factors. What does product mean? Multiply. Linear factors means all the factors are x to the first power. All right, so I'm going to move this to another screen, and then we're going to solve this equal to 0, okay? So there we are, completely factored, a product of linear factors. Now, if you want to find zeros, you need to set all of that equal to 0. Now, me rewriting this might be a little bit of an overkill, but I want you to see exactly what's going on. And then you separately set each factor equal to 0. Sometimes I get to moving a little bit too fast and I don't write this down. We just jump in there and solve. But really what's happening is I add this 1 to both sides, and I get x is equal to 1. And I subtract 1, and I get x is equal to negative 1. Here's a couple of things we got to do. We got to add 1 first, and you get 2x is equal to 1, and then divide by 2, and you get x is equal to 1/2. And then I subtract the 2 to get x is equal to negative 2. Now that's 4 zeros. Notice something about these zeros. They're all real numbers. We don't have any imaginary numbers in there, which means if I were to graph this, every one of these guys would be X Intercepts also. Also, they're nice whole rational numbers. And they're not whole numbers, I'm sorry. The 1/2 is not a whole number. It's a rational number, though. So all 4 of these guys showed up on my original list. Let me go back a page. Look at our original list over here, the top right. 1, negative 1, 1/2, negative 1/2, 2, negative 2. Well, the 1 and the negative 1 were both zeros, okay? The 1/2 was a 0, negative 1/2 wasn't, and the 2 wasn't, but the negative 2 was. But now, they're not always all on your list, because radicals, like square root of 2, doesn't show up on that list, and those are irrationals. Radicals and irrationals are the same thing as long as you can't take the square root, like square root of 5, square root of 7, okay? But in complex numbers, imaginary numbers don't show up on the list. I lost my train of thought there for a second. So there we are. We answered every question. All those guys listed are zeros, and they just happen to be X-intercepts as well. Now, problem number 11, brand new section here. We're talking about rational functions. Remember, when functions have a variable in the denominator, you have a rational function. Now, what we're supposed to do here is identify the x-intercepts, okay? That's where the graph crosses the x-axis. Now, it looks like way out here, like it might cross the x-axis, or way over here it crosses. It doesn't, y'all. That is called a horizontal asymptote. So if I put that right on top of my graph, I have a dashed horizontal line right there that the graph here approaches. As you go to the right, it approaches 0, and as you go out to the left, it approaches 0. The equation of that line is y equals 0. Remember, horizontal lines are y equals. On the other hand, look, I got a vertical line, the same thing. The graph is getting closer and closer to that vertical line, but it doesn't actually touch it. The equation of that vertical line is x equals 0, because it's right there on top of the y-axis, which is x equals 0. Now, x-intercepts, it never crosses this line, even though it looks like it slides right into it, but it's always above it. It just gets infinitely close to it. So when I ask for x-intercepts in this case, there are none. When I ask for y-intercepts from this picture, there are also none. The vertical asymptote is this vertical dashed line right here, which is x equals 0, and all vertical asymptotes are x equal a number, always, the x equal required, and horizontal asymptotes, which is written way over here. I'm just going to write HA, and that is the horizontal line, which happens to be the x-axis, which is named y equals 0. So there's all 4 answers in order. Now, the good news is we have another one of these, because the x and the y-axis sometimes makes this hard to see. So I have the same 4 questions, but a different graph. So, is there a horizontal line that this is getting closer to? So it looks like it's underneath this line right here. And it's getting closer and closer to that line. And look, if I go backwards with that line, look, the graph over here looks like it's getting closer and closer to that line as well. Now, what is the equation of that line? Well, we know it's y equals something, because all horizontal lines are y equals, but it's y equals what? Well, let's look at our scale. Notice there's 10 right there. So at first you might think it's 1, but it's not. It's 2, right? Because that's 2, 4, 6, 8, 10. So that's y equals 2. Now, is there a vertical line that the graph is getting closer and closer to? I'm going to highlight that in green. If you go down here, look, it looks like it's getting closer and closer and closer to that line. If I extend it up, hey, it looks like that's right on the upside too. Now, it should be the same thing going up or down. So pick one end and look at it, and then go the other way and see if that works out. Well, what is the equation of that line? Well, we know it's an x equals value, right? X equals what? Again, there's negative 10 right there, so that must be negative 2, negative 4, negative 6, negative 8, negative 10. Always be careful looking at your scale. So that's x equals negative 4. Now, what did we just find out here? Well, y equals 2 is your vertical asymptote, because they're always, let me say that. That's not right, right? How about your horizontal asymptote? Because it's a horizontal line, it's this one. And x equals negative 4, the green vertical one is your vertical asymptote. But I haven't answered all my questions, right? And also wanted to know the x and the y-intercepts. So if I highlight the x-intercept in purple, where does it cross the x-axis? It looks like right here. Where does it cross the y-axis? Same place, right? So the x-intercept is 0, 0, and so is the y-intercept. So my answers is x-intercept 0, 0, y-intercept 0, 0, horizontal asymptote y equals 2, vertical asymptote x equals negative 4. Okay, got another graph for you, just something to think about. The horizontal asymptote. Okay, now where is the graph, horizontal line that the graph is getting closer and closer to? Well, look, way out here, it looks like it's just riding right on top of the x-axis. And notice that goes in both directions. Okay, so that is the line y equals 0. So that looks like that is a horizontal asymptote, and it is. Okay, so that question answered. What about vertical? Now it might be, excuse me, please, harder to see. All right, But let's see if we can find a line that this graph is going up and down and approaching. Now, right here, maybe it's right there. Maybe it's not even on, you know, the line. Same thing over here. It looks like it's getting closer and closer to that value right there, but that happens to be on a line. Now, take a look at your scale again. Every grid mark is 2. So that's 2, 4, 6, 8, 10. So the one that's on the line, that's actually y equals 2. And notice how the parabola looking thing right here in the middle, it's not really a parabola, but it's shaped similar to one, how it's going down to negative infinity, and it gets super close to that line where it looks like it's just riding on it. And it's because it's so close, it appears that way. But that's just visually. It never really gets there. Same thing with going up. It looks like it's just riding on that line y equals 2. But we have a second one over here that looks like it would be a fraction because it doesn't land on a grid mark. But remember, our scale is every 2. So this is 2, 4. Right in between there is 5. So my best guess is that's y equals 5. Now keep in mind, these are just guesses. Because what if it was like 5.1 or something? You wouldn't be able to determine that. So if I were to give you this on the test and ask you to write down what you think it is, then I'm going to give you whole numbers for this, or choices, right? Okay, so y equals 2, y equals 5. Both of those are what we call vertical asymptotes. Not only that, I made a mistake. That's x equals 2 and x equals 5, right? I bet you caught that. Vertical lines are x equals. Now, we're not finished. Where does the graph cross the x-axis or the y-axis? Now, look, I need to erase right here just a little bit because I see a y-intercept. Let's make it purple. Right there. But you know what? I don't exactly know what that is, okay? It's not 1. Because it would have to be halfway up to be 1, because remember that line right there is 2. It's not 1, it's a fraction. And really I accidentally gave you a graph that it's not easy to identify the y-intercept. So the y-intercept is questionable here. If I were to give you this on the test, I would have to give you choices. But if I just had to throw out a number, I would say, you know, it's like, you know, 1/3, comma 0, or even 1/10. I really can't tell what that is at all, to the point where I almost even have to erase my dot on top of it. Remember, halfway is 1. I'm going with 1/3. That looks reasonable, okay? But again, that's a guess, and keep in mind, guessing is okay. If you can't tell exactly what it is, as long as you're close, I'm happy. Because there is no algebra you can do to figure out exactly what it is, because I didn't give you the function value. You okay with that? Okay. What about x-intercepts? So it looks like it lands right on the x-axis over here. So aren't all those x-intercepts? No, remember that's an asymptote. So it's getting closer and closer to that line, but honest to goodness, it never really touches it. Even though I swear it looks like it's riding right on the top of it, right? But that's just visually, we can't, our vision is not that acute to see that there's any distance between the x-axis, nor is a digital display enough to even show you that. You know, every line takes up a width, and the closer you get, it's just going to smack right into it, but it doesn't really. So there is no x-intercept, none, likely anyway, because that's a horizontal asymptote. Okay, now let's do some of these in reverse. Like I give you a function and you tell me back all of these things. Okay, so instead of giving you a graph, notice I have given you a function. And I want to know all those things I asked on the previous page, then some, because I want you to graph. Okay, so what is the domain of this function? Now to find the domain, what you need to do is simplify the, well, you don't simplify the function first, you just find the domain. But here's some advice right off the bat. Whenever you're given a function, I suggest go ahead and simplifying it. What's all this? Okay, so here we go. Look, there's a greatest common factor up there of a 2. I'm going to pull that out. That's 2 times x minus 2 over x plus 2. Does any of that cancel? No, please say no, 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 no. X minus 2 and x plus 2 doesn't cancel. I can't cancel that 2 and that 2 because that's part of a binomial right there. Can't cancel part of something that's added or subtracted, only things that are multiplied. So there it is, simplified. That's as good as it gets. Now, to find the domain, you set the denominator equal to 0. Or, better yet, x plus 2 not equal to 0 is what's really happening. Because when you subtract over, you get x cannot be negative 2. So the domain, it can't be negative 2. That means it can be everything else, which is negative infinity to negative 2 with a parenthesis, union negative 2 to infinity. Again, your homework might require a comma there instead of union. You don't need both. I really have grown quite accustomed to the union, but again, homework may or may not have that union symbol available for you, so a comma may work. All right, so that's the domain right here. Okay, number 2, x-intercepts. Now remember to find x-intercepts. What you do is you set the entire function equal to 0. So I have 0 equals, if you want to do the factored version you can, or if you want to do the original you can. Since I suggested you factor everything to start with, let's just do the factored version equal to 0. But what you do need to do is always use the simplified version. But this did not simplify. That's why either is okay. Now, the first thing you need to do to solve this is you've got to get your variable out of the denominator. How do you do that? You multiply both sides by the denominator. Okay? So x plus 2 times 0 is still 0. Over here on the right, those cancel, and I'm left with 2 times x minus 2. Now remember, my goal is to solve for x. So why don't we get rid of that 2? Divide both sides by 2. Okay, 0 divided by 2 is 0 on the left. 2 and 2 cancel here, and I'm left with x minus 2. Now what do I do? Add 2. So 2 is equal to x. Or if I write it in point form, remember that's 2 comma 0, because that is an x-intercept. Okay? The third thing, the y-intercept is always the easier of those two guys between the x and the y-intercepts. So you plug in 0 for x. So I just go right back to the original, okay? It's safe to go to the original or the simplified one, but we have the same thing, just a factored and a not factored. They are no different. But I'm going to write this as y equals, because that's what f of x is y. And it's 2 times 0 minus 2. Over 0 plus 2. Simplified, that's 2 times negative 2 over 2. Those 2's cancel and you just get negative 2. However you do it, and that's the answer, 0, negative 2. That is your y-intercept. Okay, now I'm going to squeeze in number 4 right here. I'm going to change colors on you so it doesn't get so hard to see what's going on. Question 4, not 3. Oh yeah, that is 4, yes. The vertical asymptotes. Now remember, the difference between domain and vertical asymptote is very small. You're supposed to simplify first. We've already established this doesn't simplify. So I'm just setting the denominator equal to 0. Also, I don't put a line through it when I'm finding vertical asymptote. I subtract the 2, and I get x equals negative 2. Now don't just tell me negative 2. You have to have the x equals with it. Because it's the equation of a vertical line. So that's your vertical asymptote. And number 5, at the very bottom, your horizontal asymptote. That's the 3-case situation. You can always look at your original problem or your simplified to do this case thing. But I'm looking at the degree of the numerator, which is 1. And the degree of the denominator, look, that's also 1. So anytime they are exactly the same degree, your horizontal asymptote, which is always y equals, is the leading coefficient of the numerator, which is 2, dividing by the leading coefficient of the denominator, which is 1. So that's 2 over 1, which is 2. If I write that completely simplified and cleaned up, horizontal asymptote is y equals 2. Now what we want to do is take all of that information and transfer it to a graph and see what we can do. Yeah, I'm going to try to do this by memory, but I may flip back to the previous page to get everything transferred. Remember, the x-intercept was 2, 0. So right on top, right there at 2, 0, I'm going to make a point. The y-intercept was 0, negative 2. That's right there. Okay. Now, I don't want to do my horizontal and vertical asymptotes in the same color. Now, if you're using a pencil, of course, you're going to do the same thing. But what I need you to do is do a dashed line for your horizontal asymptote and vertical. So we had a vertical at negative 2, and x equals negative 2, and a horizontal at 2. So a vertical asymptote at x equals negative 2. So I'm going to do a dashed line at x equals negative 2. Now what's important about that is the graph can never ever cross through a vertical asymptote. Now the horizontal asymptote was y equals positive 2. Now horizontals, sometimes the graph does intersect a horizontal asymptote, and I will show you how to solve the equation to find out if it does cross over the horizontal asymptote, okay? So here we go. Let's plot some points. Remember, the rule for plotting points is that you plot between and beyond every x-intercept and vertical asymptote. Okay, so I'm doing a t-table, x column, y column. Now you're working left to right, so I need something to the left of this vertical asymptote at negative 2. Something to the left might be, by the way, negative 5 is right here. It's so confusing when it does that, and positive 5 is right here. If you start counting, remember that's negative 1, negative 2, negative 3, negative 4, negative 5. So I can't control where they put those numbers, so it bothers me sometimes. But anyway, so let's plug in, say, negative 3, even negative 4. I'm going to do negative 3. Okay. Now I need something between, this vertical asymptote and this x-intercept. You know what? We already have something there. It's 0, negative 2. Okay, it's already a point there. If you wanted to plug another point in, negative 1 or positive 1 would be perfect. Then I need a point on the other side of this x-intercept. For instance, 3 or 4 or 5. I'm going to plug in 3. Okay, now notice this isn't simplified anymore. If this had simplified and canceled, something canceled, truly simplified, I would use the simplified version. We did have it factored, and it doesn't matter if you use the factored version or the original version, whatever you feel better about. You just got to plug in negative 3. So that's 2 times, I'm going to use the original, 2 times negative 3 minus 4 divided by negative 3 plus 2. 2 times negative 3 is negative 6, minus 4 is negative 10 in the numerator, and negative 1 in the denominator. It gives me 10. You know what? You might be looking at my scale and going, she didn't give us a 10. That's okay. That's okay. We'll figure this out. So I'm going to plot the point negative 3, 10 in a minute, but let's go ahead and plug in 3. So it's 2 times 3 minus 4 over 3 plus 2. Again, my x is 3 in both of those positions. 2 times 3 is 6 minus 4 is 2 in the numerator. 3 plus 2 is 5. So that's just a little number 2/5. Now if I go back to I was plotting in green, so let's do green again. Negative 3, 10. So negative 3. Now I'm just going to put 10 like way up here. I know that it's really higher than that because if this is 5, then 10's double that. But we're just trying to get a general shape here. And then the point 3 2/5. So this is again 1, 2, 3. Remember that's 1. So 2/5 is about there. It's less than half. So that's what we've got going on. Now let's look at what we have. You might not feel like there's enough over here, but you know what, there is. Because remember, from your point, your graph has to approach the horizontal asymptote in curved form, and it has to approach the vertical asymptote. Now, verticals, it either goes up forever or down forever, but it can't go down because we didn't have an x-intercept right here. Okay, our x-intercept's way over here, so it must go up forever. And then that's that piece done, close enough anyway. Over here, the graph, okay, so from here, it's either got to go up this way or down. Look, it goes down, right? It can't go up because that means it would cross the x-axis around here somewhere. And it can't. It only crosses the x-axis right there. So I cross over and I approach the horizontal asymptote. Now, there is a really good question I said I would address. Does the graph cross the horizontal asymptote? Most of the time they don't, but let me show you how to find out. You take your horizontal asymptote, which is 2, and you set it equal to your function, 2x minus 4 over x plus 2, and you solve that equation. Okay, so you learned this in a previous math class. I multiply both sides by the denominator. Okay, now over here, that doesn't cancel. I got to distribute the 2 inside. So that's 2x plus 4 is on the left. And then on the right, it's 2x minus 4. Okay? Then to solve for x, I need my x's on both sides. So I'm going to subtract 2x, and then you notice something happened. My x's cancel, and that tells me 4 equals -4, but there's no solution to that. You know what that means? It doesn't cross. If I got an answer for that, that's where it would cross, at that x value, but I got no solution, so our graph is right. It's never going to cross this horizontal line in this particular case. You never have to find out if it crosses vertical, because it doesn't. The graph is undefined there. Let me try this again. Let's try another one. Okay, now here we go again. This almost looks just like the last problem. Is it 2x plus 4 over x minus 2? 2x minus 4 over x plus 2 is different. Notice I just changed things up just a little bit. I had to be sure, just to make sure. All right, so this is a different problem. So we're supposed to find the x-intercepts, y-intercepts, vertical asymptote, all that good stuff. So again, my advice, always simplify first. 2 times x plus 2, I'm factoring out a greatest common factor over x minus 2. Does anything cancel? No, just like last time. All right, so for the domain, I'm supposed to set the denominator not equal to 0. That means x is not 2. So if I write that in interval notation, this is what I get. Okay. And that's it. Now, if you need a better explanation of that, I say watch problem 12a, in case you didn't watch that, because I go through that in a little more detail. But domain, set the denominator to not equal to 0. If this were to simplify, do not simplify it before you find the domain. And because you need to know everywhere the denominator is 0, even if something cancels out. And we will get to a problem like that. All right, next we're supposed to find the x-intercepts. So x-intercepts, you set the entire function, either the original or the factored one. If it's simplified, you would use the simplified. So simplified equal to 0. Again, this did not simplify, so I don't do that. So simplified equal to 0 means 2 times x plus 2 over x minus 2 equals 0. Or you could go with 2x plus 4 over x minus 2 equals 0. Okay, because one's not simple. It did not simplify. I'm getting tongue-tied. Okay, x minus 2's cancel. So now I'm left with 2 times x plus 2 equals 0. I'm trying to solve for x, so let's divide both sides by 2. That gives me x plus 2 equals 0. Subtract 2 from both sides. That gives me x is equal to -2. Now remember, this is an x-intercept, so this should be in point form. That's my x-intercept. My y-intercept is when you set x equal to 0. I'm going to write that as y equals, and you can plug in that 0, always in the simplified one, but again, these are the same, exact same. One is factored and one is not. So 2 times 0 plus 2 over 0 minus 2. So when that simplifies, that's 4 in the top and -2 in the bottom, so y equals -2. So that's the point 0, -2. That's my y-intercept. Can change colors on you and work on the vertical asymptote. Now the vertical asymptote, just like the x-intercept, you always want simplified denominator equals 0. Okay, well this didn't simplify. The denominator stayed x minus 2 equals 0. This is your vertical. That gives me x is equal to 2. Okay, what about horizontal asymptote? That's the 3 cases. I'm looking at the degrees, right? The degree of the numerator is 1. The degree of the denominator is 1. Whenever that happens, your answer is y equals, and then its leading coefficient of the numerator. Let's do this bright pink. Leading coefficient of the numerator is 2. Leading coefficient of the denominator is 1. So I write my horizontal asymptote as 2 over 1, which is 2. Or you could say y equals 2. Now what I want to do is take a second, transfer all that information to a graph, plot points, and see what we get. So the first thing I did is I plotted it -2, 0 right here as my x-intercept, and then down low 0, -2 is my y-intercept. Remember, we've got vertical asymptotes, right? One of them was, and let's go back and look just to be sure, vertical asymptote x equals 2, horizontal asymptote y equals 2. So I go back to my page in green, have a vertical asymptote, dash line, okay, vertical asymptote, dash line, get my green working properly, at x equals 2. There it is, and a horizontal asymptote at y equals 2. Now, what do we know? The graph can never intersect this vertical line. It might intersect the horizontal. If you had to guess, it probably won't, but some graphs do. Okay, we haven't really talked about the nature of what those graphs look like because that gets into pretty deep detail. Just graph it and find out, and we have a trick, and we'll talk about the trick in a minute. So I got to plot points. Now look, I've already got 2 points over here. As a matter of fact, look, that's enough, y'all. You can tell that as you connect right here, it's got to be a curve. It's not going to be a straight line when these connect. It's going to be a curve, and we're going to approach the vertical asymptote. Now it could flip up, except we don't have an x-intercept over here. It's over here. So it crosses here, and it approaches the horizontal asymptote. That doesn't look nearly as smooth as it ought to. It's not all wavy in here, folks. It's a lot smoother than that. So if I erase some of this and try to make it perfect, it's still not going to look perfect. But I'm going to try to make it look a little bit better there. Okay. Now the other side, look, there's got to be some graph over here on the right also. Thing is, I don't know if it lives up here in that square, like first quadrant story, or if it lives down here in like the fourth quadrant situation. So what I need to do is plot some points, okay? 1 or 2 will be great. Remember, this is x equals 2. So 3 or 4 or even 5 out here at the end, I'm going to plug in 3. So here we go. So x, y, let's plug in 3 for x. So what am I going to do? I'm going to just plug it straight in the problem. Now, if this simplified, I really would rather plug it into the simplified rational function, but this one didn't simplify, nothing canceled. So 2 times 3 is 6 plus 4 is 10 over 1. Ha, we get 10 again. Again, too big, right? Is that okay? Oh, it's fine. So 310 is way up here, but that does tell me that the graph lives up here and approaches the horizontal asymptote and approaches the vertical asymptote. Okay? Now, if I go back and re-put this graph in here for you, I'm not doing this in real time. I've already put the graph in here before I ever built this PowerPoint presentation. I'd probably put more of a scale on it, but I just kept it to 5 to 5, and that works pretty well. Okay? All right. I'm going to close out this video because this part 3 is getting really long, and I'm going to move on to a part 4, and then we'll try 12C beginning part 4. Have a good one.